discussion about fixed versus random effects, which we started talking about, but I promise there is a whole lecture that's going to be dedicated to those mixed models. Were there any questions from Tuesday? So to start off, as sort of administrative announcement, the homework assignment has been posted on Blackboard. Right? So there's a data set out there called Regress.bat. It's a text file, and it'll look much like the, it's basically, you have to do the same thing that you had to do from the SPADA lab instructions to read that data set. And then there's 5 variables in there. One of them is just a subject number. Another one is the number of times someone went to the doctor, so think of that as utilization. Another variable is an index of physical health. Another variable is an index of mental health. And the 5th variable is an index of stress. Your job is to predict utilization, the number of times they've been to the doctor, based on mental health, physical health, and stress. Now, what I'd really like you to do for that assignment is to pay attention to the assumptions of regression. And after you do all that, after you do your analysis, what I want you to do is write it up. So I want you to write it up in such a way where you explain to me what you did, but not only what you did, but why you did it. Right? Because I really want you to take the time to think about what it is that you're doing and why you're doing these things, as opposed to thinking of statistics like a meat grinder. You take data, you put it to the meat grinder, you get unanswered. We need to stop thinking that way. And then, after you do that, I want you to write up your results with a lay audience in mind, right? With a lay audience in mind. Pretend that your audience are lay policymakers who don't necessarily understand statistics, all right?
Grandma.
Huh?
Grandma.
Oh.
Grandma.
Yeah.
Dear grandma.
Except for Lisa's grandma.
Except Lisa's.
Okay? Does that make sense? The reason I want you to write it that way is because we need to take the time to slow down, because I know you guys pretty well. Slow down and think. Think about what you're doing. Think about why you're doing it. Based on your results, what are the implications of what you see in the data? Okay?
Can we work with a buddy?
Absolutely, cheat. I'm encouraging cheating.
And is
Yes.
it due after spring break?
Pardon?
Is it due after spring break?
Yeah.
Cool.
Yeah. It's not due per se, because as we said before, but we'll review them together. Okay. Okay? Because it's a data set that, it's an interesting data set that it's the kind of data you might see in the kind of research that you guys do. But there's some interesting things about the data. We'll see if you pick up on them. Okay? All right. All right. So let's pretend we didn't do any of the stuff with respect to the data analysis on Tuesday. So all I'm going to do here is I'm going to read in a data set, and then what I'm going to do is I'm going to give every patient or every observation a unique identifier. In this data set, there is no unique identifier. But the reason I want a unique identifier is because further on down the road, when we look at something called Cook's D, Cook's D is an index of multivariate outlierness. It's going to tell us which observations are goofy. Okay? And then what we're going to do is we're going to examine well, that's much better. We're going to examine the univariate statistics. All right, so in your write-up, whenever you do data analysis, whenever you get data, what's one of the first things that you should be doing? You should look at your data, right? So why do we want to look at these univariate statistics?
You want to see how it's distributed?
Right, but why are we interested to see how it's distributed? These are all good answers.
To see if there's any missing values or
Right.
outliers.
Outliers, missing values. We're using our brains, our subject matter expertise to try and determine if these data are reasonable. See if the data are reasonable. do that make sense? If we have missing data, that will have implications, because what will happen with most software is that it's going to perform what's called case-wise deletion. It's going to just drop the observation if it has a missing value. Okay? So you're throwing information away. Okay, then we're going to do this little thing. Does anybody remember what this thingy's called?
Blot.
Spoon.
Splot. Like a splot. This is our splon, right? Our scatter plot. Our scatter plot matrix. And what are we interested in these? So what does this graph represent here? What are these things?
Bivariate correlation.
Bivariate correlations. They're bivariate scatter plots. And why would we be interested in bivariate scatter plots when we do multiple regression?
Because you want to make sure that everything is relatively independent. So if you look at this, you look at the one between size and age, it looks like there's possibly a high correlation that may be something you need to look into.
Right. What's that thing we may need to look into? Does anybody remember the name of that?
Is that like multicollinearity?
Multicollinearity, right? Multicollinearity, right? The other thing that we're looking at, in some sense, is are the variables, are our predictors related to the outcome? Right? Because remember we drew what a suppressor variable looks like? We drew what a suppressor variable looks like. Right? So we want to be on the lookout for suppression. All right? So after we do that, we can actually examine the correlations. Examine the correlations. So here we see the association between height and IQ is nearly 0. The association between weight and IQ is nearly 0. So all these things are pretty small except for age. Yeah? Okay. Right, but we have to keep in mind that these are bivariate correlations. We know what happens when we put these things together to create that linear combination, right? Right? Those semi-partial correlations, we know that the magnitude of the correlations can change and signs can flip. All things can go fluid, right? But these are things that we want to keep an eye on. Okay. And then we're going to do our yes, sir.
Is this code online?
You want me to put it there?
Yeah, just because.
Okay. Like maybe I have to do a homework assignment that looks eerily similar? Sure. Good. Do you have a handout from Tuesday?
Oh, okay, sorry about that.
I'll put it out there, so no problem. All right. So now we do our regression. So, all right, so for those of you who don't remember, to do the regression in Stata, the command is reg, or regress, and then we're going to regress the first variable onto our predictors. Okay, so in this case, we're trying to predict IQ from height, weight, brain size, and age. Okay? So after we do our regression and we get this output, what's one of the first things we want to look at? Anybody remember?
Do you start with the F statistic to see if...
With the F? Yeah, why do we want to start with
Just
the
to
F
see
statistic?
if that's basically saying whether this is better than nothing alone.
Right. So we're going to look at this F statistic here based on 4 degrees of freedom in the numerator here. Why 4? Because there are 4 parameters we estimated. And 2,896 degrees of freedom in the denominator. So to get this F statistic of 3811, you're going to divide the mean squares for your model divided by your mean squares for residual. Or if you did this by hand in intro stats, you would probably call model your between and your residual your within. These are all synonyms for each other. Okay. Okay, so we have an F statistic of 3811 with that orgasmic p-value there. And how do we interpret that?
That this is better than nothing.
It's better than nothing, right? Okay, then what else do we want to look at?
R squared to figure out how much of the variance is explained by your model.
Okay, and how much variance do these 4 variables explain? How much variability in IQ do these 4 variables explain?
5%.
About 5%, right? Is that a lot? I don't know, it might need context, right? You need context. Right? And this adjusted R square, I'm saying that we can ignore it, but if anybody asks, does anybody remember what the adjusted R square is? What is it adjusting for?
How many things you put into the model?
The complexity of the model, the number of predictors, right? Okay.
You always just use regular?
Yeah, I always just do regular R squared. Now, let's talk about the discrepancy between this tiny, tiny p-value and this R squared of 0.05. Anybody have any insight as to why our p-value is so very small and so is our R squared? Any insight into that?
Has it got something to do with the number of observations?
Yeah.
Because the denominator is it the square root of?
No, the denominator is going to be, this is the within group variance, right? The error variance is tiny. The within group variance is so small because we have nearly 3,000 observations. So we might want to think about the distinction between statistical significance and practical significance, right? So to really interpret this R squared above and beyond, it explains 5% of the variability in IQ. To interpret that contextually, you really have to know a little bit about the literature. How have other models fared? Have other researchers or other investigators, have they come up with models that explain more variance, less variance? Right? Because if the next best model explains 1% of the variance, has an R squared of 0.1, this is a rock star regression. Right? This is a remarkable regression. This is a quantum leap forward in your learning about whatever it is that you're studying, even though you're only explaining 5%. Right? It's still 500% more than the next best model.
Could you go over again why they're related, why they're both so small?
Well, okay, this is small. Well, let's talk about the F statistic.
Because the F is so big.
The sample size is so large. When we have very large sample sizes, we're going to find very small differences to be statistically significant because remember we're testing is the difference 0 essentially, and the central limit that this is driven by the central limit there.
Well, why does that make the R squared also small?
That's independent.
But weren't you just saying that they're both so small?
Well, what I'm saying is that this is small and this is small. Let's talk about why that is. They just happen to both be small.
Okay, but they're not related.
They're not related.
Small.
Right, so which is a good point because we talk about this R squared as what we refer to as an effect size. Right? We talk about effect sizes being relatively invariant to sample size. Right? So from my perspective, this R squared is far more informative to me than is this very small F statistic, p-value. Right? This is a very small F statistic, p-value, probably because the sample size is so large. In some sense, we have overpowered the study. Right? We've overpowered the study in that sense. So the R squared is small. Why? Do you have any explanation as to why that R squared might be so small? Because they're crummy predictors. Right. They're not very good. I bet we can probably predict using other variables that predict IQ a whole lot better. Okay. And then we have this root MSE. Does anybody remember what MSE is? Mean square error. So what is that? That's the standard deviation around the regression line, right? So we know that most of the dots are not going to fall directly on the regression line, right? And the distance from the dot to the regression line is the error. So we have to have some standard deviation of that error to talk about how much variability there is around the regression line. That's the standard deviation, or estimated standard deviation of regression. Okay, so let's talk about these things. So here, the way Stata sets this up, I'm going to give you the column headers, and then we'll take these in turn, okay? So the IQ, the first column is always going to be labeled the name of the criterion, right? It's going to be the name of the criterion. So these are the parameters. These are the parameters, the names of the parameters that we're interested in. These are our regression coefficients, right? So those are the B's. The B's are the beta hats. This is the standard error of these coefficients. So whenever you hear the word standard error, you think a standard error is a standard deviation of a sampling distribution. So this standard error gives us some sense as to how much variability there is in this coefficient, in this parameter estimate. This is the t-statistic. And I get that t-statistic by dividing the coefficient by the standard error, just like you did when you did a independent or dependent samples t-test. Right? So if we were to write this out, it would look kind of sort of like a z-statistic, except it's a t-statistic. Right? But I haven't told you what we're testing yet, so we'll talk about what that is. This p-value is associated with this t-statistic, so what is, well, I'll do what that is. I'll let you guys describe to me what that p, how to interpret what this p-value is. Then we have the confidence interval around the coefficient. So this 0.96 should fall right in the middle of these two numbers, right? Okay. So who wants to take a crack at in trying to interpret height, the effect of height?
For every 1 unit of height increase, we would expect a 0.96 increase in IQ.
Right.
I don't know how to talk about this. I'm going to skip to the T.
That's fine, that's fine.
Okay, so our T statistic is 8.54, which is high.
What are we testing here with this t statistic? Anybody know what we're testing? If I were to write a null hypothesis for that height parameter, what
But
is
there's no relationship between height and IQ.
so how else would I say that statistically? That's right for grandma.
Comparing two means.
No, we're not comparing two means in this case. So this is regression. Remember, y equals mx plus b. What is m in that case? Slope. So if there's no relationship, what do we expect that slope to be? 0. So we're testing to see if that slope is 0, because if the slope is 0, that means no association, right? Good.
Can I ask a question? Is it a 0.96 increase in IQ or a 0.96 increase in height?
Okay, she said it right. Want to say it again?
For every 1 unit increase in height, we expect a 0.96 increase in IQ.
Right, so this is an expected change in y for every 1 unit change in x. Right? Okay. Is this this 0.96 you said, we're missing a little bit in that interpretation.
Holding weight, size, and age constant.
Holding weight, size, and age constant, right? That's important. Okay. And how about these confidence intervals here? How would we interpret this? Which, by the way, confidence intervals are probably, next to p-values, are probably the most misunderstood thing in statistics. So like we were talking about with Lisa on Tuesday, if you don't know, that's okay, that's why we're here. Right, so take a shot at it. Anybody want to take a crack at how to interpret those confidence in a confidence interval?
I think it means that you can be 95% confident that the true value lies within that range.
Okay.
Close to that.
Something like that, okay, all right. I like to think about confidence intervals, excuse me, as my set of plausible values.
If you did it a number of times.
Pardon?
If you repeated the model a number of times.
Yeah, so technically what a 95% confidence interval is If you were to repeat your experiment an infinite number of times, you would have an infinite number of confidence intervals. 95% of those 95% confidence intervals would include the true parameter. If you had a 99% confidence interval, 99% of the 99% confidence intervals would include the true parameter. But you can't say there's a 95% probability that the true number is in this confidence interval, in that particular confidence interval, because either the probability is either 0 or 1 that it's in that confidence interval. And that's why these things are confusing, because we talk about probabilities versus confidence. They're different. All right? So here I like to talk about these things as, this is our set of plausible values. So a good way to interpret this might be, well, our best guess as to the effective height on IQ, holding these things constant, is about 0.96. Could be as low as 0.74. Could be as high as 1.2. So we're giving ourselves boundaries. Could be as high as this, could be as low as this. Make sense? Okay. Who wants to take a crack at interpreting height? Or sorry, weight?
Similar with every 1 increase in weight, we expect a 1.9 increase in IQ.
Okay.
Which also which has a higher t-statistic and still a significant p-value.
Right.
And that 95% of the time, I still don't exactly know how to send words. I get that, like, if the study were to be repeated,
Right, so that's why I like to go with
95% of the time.
All right, so that's why I like to go with, it's our set of plausible values. That's more intuitive.
So you say with a set of plausible values?
This is our set of plausible values.
Of 1.5 to 2.2.
Yeah, anything within that range we say is a plausible value. Okay, good. All right. Now, how about this constant here, right? This underscore cons. Underscore cons. What is this? This is our y-intercept.
It's expected value of y when all of it is 0.
When all of those values are 0. Now, would we expect anybody to have a 0 height, a 0 weight, a 0 brain size, and 0 age? I guess we won't get into the philosophical or you're right, we won't get into the religious discussion as to when that starts. Because at that point they would then have some height and some weight. As small as it would not be 0, right? Okay, so here, in general, though, if we tend to leave our variables as is, we don't do anything with them. In general, the intercept is generally it's not of any consequence. It's not of any consequence. But next Tuesday, I'll show you how we can manipulate our data such that these coefficients do not change, but we get a meaningful constant. Right? I'll show you how to do that, which in a lot of cases is informative. Because if you were interested in the average person, right, the average person, then that constant, we can make the constant represent the average person. So the person at the average height, the average weight, the average brain size, and the average age simultaneously. So it's a multivariate average person. I'll show you how to do that.
Can you just put towards again the t-statistic?
Pardon me?
Just like how you explain like this 8 is a high number. But
Okay.
again,
Okay, yeah, all right. So this gets back to null hypothesis statistical testing. So I'll come over here. So we have a t-statistic, or a t-distribution. And the t-distribution is going to be based on 2,896 degrees of freedom. So this t-statistic, TEF 2,896, right? This is going to have a mean of what? Every t-distribution has a mean of what? 0, right? And what else do we know about a t-distribution? It's normal-ish, which means it's symmetrical around 0, right? And the other thing that we know is as the degrees of freedom increase or approaches infinity, what happens to the shape of a t-distribution? It becomes more and more normal. It looks like the standard normal distribution. So with nearly 3,000 degrees of freedom, that's essentially infinity for this t-distribution. So at roughly 1.96 and roughly positive 1.96, we're going to expect what percentage of the scores to fall within that range? About 95% of the scores, right? We observed a t-statistic of 8, 8.5. So that's way out here, right? So we can take this t-distribution and we can chop it up into 3 regions, right? So if we observe a statistic, a t-statistic below what we refer to as our critical value, and in this case, let's assume we have an infinite number of degrees of freedom, the critical value would be plus or minus 1.96. So we would draw goalposts, right? So think of this as a football field, right? How far do you have to go onto a football field before you score a touchdown? On this football field, we have to go at least 1.96 units away from the midfield, right? So we're way out here at 8.54. So this is a deep fade route, if you understand football parlance, right? So this is way deep in the end zone, right? So if we observe t-statistics out here in the tails, we're going to reject the null hypothesis. If we observe a t-statistic within this range on the field, not in the end zone, we haven't scored yet. So we're going to fail to reject our null hypothesis. Okay? So what happens here is that if our null hypothesis were true, if this t-statistic was, if the real coefficient was 0, the probability of observing a coefficient this big or bigger, the probability of observing a coefficient this big or bigger is going to be less than 1 in 10,000, right? The reason I say this big or bigger is because it's the area outside, the whole area, right? And since we're going to do a 2-sided test, meaning this could be either positive or negative, right? We have to look on both sides of the football field. Right, so that says, what's the probability I observe a statistic this large with an absolute value this large, assuming the null hypothesis is true? Okay, so are we happy with these results so far? What do you guys think? A lot of people would probably declare victory, walk away, and start writing up the results. Right, and go, yay, tiny p-values. Tiny p-values must be good. But you know better. We got to do some digging. Okay. Oh, we haven't done that yet. What we're going to do next is we're going to look at the standardized coefficients. Right, so to do that, we're just going to do reg comma beta. And it's going to give us these beta coefficients. Right? So if you remember from last week, or last time we met, the beta coefficients are standardized coefficients. So if I want to compare the relative effect of one variable versus another, they have to be on the same metric. Right? Because if I have one variable that has a huge variance in it, its coefficient is probably going to be very small relative to something that doesn't have a lot of variance in it. So these are beta coefficients. And how we could do this is by turning everything into z-scores. Right? That's how we make everything on the same metric. So then we can compare one thing to another because it's all standardized. Okay, so now, since these are standardized coefficients, the interpretations of these coefficients change relative to these coefficients. Whereas before we said for every 1 unit increase in height, so let's say height's measured in inches, for every 1 inch increase in height, we expect IQ to go up about 0.96 points. The interpretation of this changes with these standardized coefficients. When we standardize the coefficient, what is the unit that we're dealing with here? Standard deviations. So the interpretation of the beta is for every 1 standard deviation increase in height, because that's the unit we're dealing with here, we expect IQ to go up 0.21 standard deviation units. Okay? And because we know standard deviations are measured on the ratio scale, remember nominal, ordinal, interval ratio, right? We can talk about the relative effect of these, the contribution of each of these variables, or what is the effect of these variables on the outcome. Right? So here, let's look at the effect of age. That has a beta of 0.83. That's pretty big. That's fairly large. It's actually about 4 times as large as the effect of age. I can do that by just dividing the big coefficient by the lower coefficient. We can do that because these are ratio variables. Right? So now we can rank order these things in terms of absolute value, because I could have a negative beta too, right? Okay, so if I were to rank order these in terms of absolute value, I could talk about the importance, the relative importance of each of the predictors. And I think that's where we left off on Tuesday. Okay? So what's new here is, it's actually not new, we're still...
Can I ask something?
Yeah, sure.
You have to know something about your data set, though, to even interpret that, right? So
You don't have to know
age-
anything about your data set to do anything.
Right, but like your age range could be 50 years, in which case one standard, I mean, you have to know what standard deviation unit is in any of those variables in order to...
Yes. Which is why we do that first thing of understanding our data, doing that model conception. Right? This is just like a patient. I mean, it is. And what you guys do is when somebody presents is you follow the scientific method, right? Did we do this before? Right? Observation, codification, hypothesis generation, test the hypothesis, do it over and over. You do the same thing when you see a patient. Patient comes in, what do you got to do? You got to observe them. Right? You got to come up with a preliminary diagnosis, case conceptualization. Then you got to come up with a treatment plan. Treatment plan is going to be based on your hypothesis. Then you execute the treatment plan. Did it work? Right? It's the same thing. So just because we're dealing with numbers, it's the same concept. Here we're diagnosing things. To do that, you have to know about what you're looking at. Okay, the next thing we might want to look at are these partials and semi-partials, right? These partials and semi-partials. Anybody want to take a crack at that? Well, if I were you, I'd be interested in looking at these semi-partial squares. These semi-partial squares here. Right, so let's take age, because remember that was the biggest. Right, how would I interpret this squared semi-partial correlation of 0.5? Okay, all right, I'll give you a hand. The relationship, or the unique relationship between age and IQ holding these things constant, or age has a unique relationship of about 5% between, with IQ, holding height, weight, and size constant. One thing that you'll notice is that the rank order of your semi-partial correlations will match the rank order of your betas. Holding these things constant, height, weight, and size, brain size, age explains about 5% unique variability. The unique amount of variability that age explains in IQ is about 5%. Or IQ explains 5% of the variance above and beyond what height, weight, and size, brain size explains. These are all the same way of saying the same thing. So if you were to write this up, sorry, go ahead.
So your R squared in the top half just tells you that there is a significant relationship, and this kind of quantifies it.
Yeah, so this R squared, you're talking about, oops, sorry. This R squared here?
Oh, no, sorry, I meant the beta coefficient. I meant to say the beta
Here.
coefficient, yeah.
Yeah, yes.
Okay, so you can't have a significant t statistic here.
Sure you can. The t statistic
And
for
then-
this is exactly the same as t statistic for this.
Okay. Oh, okay, never mind.
Yes.
A stupid question, but.
No stupid question. Ask more questions.
Because I know I can answer my own question if we go back to the Venn diagram pictures, but if you just look at the table above, like if you're looking at explaining what the coefficient is,
These.
you're saying height goes up by, for every increase in height of 1, your IQ goes up by 0.96, holding the others constant, right?
Right.
So if you look down at the semi-partial correlation squared,
Yeah.
you're saying the unique relationship between height and IQ holding the others constant. Like, how is that? I feel like we're explaining, the English explanation is not that different between the two.
Well, right. So in the regression coefficient, you're talking about the absolute magnitude of the relationship between the two variables,
Right.
holding the other things constant,
Okay.
right?
Yeah.
So you're talking about inches in height and IQ points.
So they're saying they're all indifferent.
Yeah.
Right.
Where the regression coefficients are in their original metrics.
Right. Okay.
Here, it allows us to look at the relationship between the two things in a correlation metric.
Okay. So all, like, similar to the beta.
Data similar to the betas.
But,
Okay.
but how do you conceptually think about this in terms of the R squared? Overall, the R squared explains 5% of the variability in IQ.
Right.
The age alone
Right,
explains
seems like you're
5%.
jumping on something.
Is it because there's multicollinearity that
No, and here you have removed the collinearity.
but how can age explain 5% of it? Size explains 4%.
Because, that's a great question. So this gets back to the understanding of the partial and the semi-partial. So I have to I'll write down the model again, right? And then we'll explain what these things are, okay? So the model that we would write is this. Right, okay? This is the model that we've written down for multiple regression, right? So that R squared up top with the regression model is the correlation between this value, between the observed value, and the predicted value. So it's really a bivariate prediction. So this component of the model creates a y hat. That R squared is a correlation between yi and y hat. That's all it is. Whereas these semi-partial correlations, here we have y, x1, x2. The semi-partial correlation is the correlation between y and x1 prime, where we have removed the effect of x2 from x1. So it's no longer x and y, it's x1 prime and y. That's what that semi-partial represents, whereas the R squared represents the association between y and y hat. Does that make sense? They're different things.
I think what still is weird is that it seems like this is trying to say we explain more of the variance in Y than.
It's the unique variance That's why I said that to explain this is that age explains the unique amount of variance that age explains is 5% above and beyond what these things explain. So it explains 5% more. Not in an absolute value sense, it's a relative sense.
Whereas your R squared, or the correlation between y and y hat, that's how much your model,
Right.
the whole thing
The whole
together
thing
is
together.
explaining the variance of your outcome.
Right, so if we were to go back up top, you remember we can get, does anybody have a calculator? Are we going to get the R squared here? We're going to divide 152.63 by 3052.63. So divide the model sums of squares by the total sums of squares. It's going to be about 5%. Right? So this model sums of squares represents the whole expected value. Whereas age, after removing the effect of height, weight, and size, age will explain about 5% of this. If that makes sense.
So then, if you add up all the percentages in the semi-partials, can you get a sense of?
No.
No.
Because they're
Meaningless
different.
number?
Yeah, it's meaningless.
Okay.
Okay.
Because it's like each one holds the others constant.
Right,
so
whereas
it's
the other
not-
one is, yeah, exactly.
Okay.
Okay. All right.
Could you write up in terms of, like, we have the equation for the model for the regression coefficients.
Mhm.
Could you review the equation that goes with the semi-partial coefficients?
You're going to write down the whole equation?
It's super long.
I don't remember it off the top of my head.
Okay,
It's kooky.
okay.
There's a couple of ways you can do it, but think of it this way, okay? Another way to think of it, to get this 5%, to get this 5 here, right? If I regressed IQ on height, weight, and size, I get an R squared. How much higher does that R squared go when I then include age above and beyond those things? It's going to increase by about 5%.
So if you didn't have the betas to compare to and you just went with the semi-partial square, could you interpret that as saying that age has a bigger effect than
Yeah.
the
Holding
Oh, yeah.
the other things down, yes, absolutely. Yep, okay.
The partial correlation squared and the semi-partial correlation squared numbers are almost the same,
Mhm.
but not quite the same.
Yeah, that's just because of this data set. It's a fictitious data set. Made it up.
So the beta coefficients, you can say the absolute magnitude of the relationships between each, but you can't say which one affects the outcome
Not for
more
the
than the
betas, for the
other.
regression coefficients, yes.
Okay.
For the
And that's
regression
why you need
coefficients.
the.
So this is the relationship between height in inches and IQ points, holding these things constant.
But I couldn't say, looking at this, that say
Yes.
size has a greater effect
Yes,
on weight, which is
exactly.
what we're saying
Exactly.
with the semi-partial correlations.
Exactly.
Okay.
That's exactly right.
Okay.
It's difficult to interpret these, the raw coefficients,
'Cause they're
because
not
they're all in different
standardized.
metrics.
Okay.
Exactly.
So both the beta and the semi-partial, you can compare with.
Yeah, because they're in standardized
Right.
metrics. Yeah, exactly.
Can you go back to the standardized metrics for this one? Is that like standardized deviation unit really like the standardized deviation when we do that initial? That's exactly what it is. So
For
every
why it is. For why it is. In height, yes, yes, so
for
yes.
each one, it would be like the standard deviation that we get of height when we calculate our variables is
Yes.
the standard deviation unit
holding weight, size, and age constant, yes.
So all of your independent variables in this model are your continuous variables. Can you roll this like with your independent variables?
Absolutely. When we do ANOVA, we're going to do ANOVA both using the ANOVA commands and the regression commands, and we'll show you that they're the same thing. And you can mix them. You can have a mix of continuous and categorical in regression. Okay.
And then, so semi-partials are explaining the amount of variance, and betas are standard deviation?
Yes,
or something? Is
yes,
that-
yes, yes.
But they're explaining the variance in standard deviation units.
The betas are,
Right.
yes.
So why, would you have to do both? Would you ever do just betas plus anything? They just compare the variance?
Well, you could talk about this in terms of rank ordering them, right? Or you could just do the semi-partials and you'll get the same thing.
Right.
But here you can't talk about the relative importance. But I mean, with these you can't talk about the relative importance, right? Because this is only twice as big as height is, or age is only twice as big as height. But for here, it's 4 times as big, right? So it depends what kind of things you want to say. You could rank order them and say this is most important, this is second, third, fourth, in which case you could either look at the betas or the semi-partials, because the rank ordering will be the same. If you want to talk about the relative magnitude of the contribution, betas. So this gets back, remember we talked about in the very beginning, and I harped on it for a while, what's your question? What exactly are you trying to say? You can, remember I announced, this is a very sophisticated tool that we're wielding here. And there's a lot of information that we can extract from it. But you have to know what your question is.
So why would you do semi-partial?
I like semi-partials because it tells me the unique contribution. Right? Remember we broke them up into like demography variables and then say other medical variables and then the variable of interest, right? Okay, so we did that. Okay, so here's some interesting looking plots. What we're going to do is, Stata is really good for regression because it has a lot of plots built in for you to be able to do these diagnostics. So the next command we're going to execute is called AV plots. Stata calls them added value plots, AV for added value. Most statisticians would call these partial plots. So let me run this and we'll see what this actually looks like and we'll explain what this is. Okay, so let's look at this. And this is really cool in that it does this for you. So what does it mean to partial something out? We get back to the idea of what does it mean to partial something out? Not semi-partial, but partial.
So you're taking out one of the effects of one of the independent variables on the other independent variable and the dependent variable.
Exactly. Right? So in this case, we have height. We're interested in looking at the relationship between height and IQ after we have residualized height and IQ using weight, age, and brain size. Right? So this is the bivariate correlation between height and IQ holding these 3 things constant. Why am I interested in looking at this? I'm interested in looking at it because I might be interested in only one of these variables in particular. For example, I might be interested in, I don't know, age. Right? What's the relationship between age and IQ? I'm interested to see if I see this linearity assumption, because if I partial everything out and there's no relationship, this regression line, I don't know if you can see, but there's a green regression line here. The green regression line would be flat. Right? So we want to examine what is the magnitude, the strength of that relationship after holding everything constant. So after we've regressed, we've partialized everything. So think of this as height prime and IQ prime. This is the scatter plot. Right?
regression lines different? Are those regression lines different?
Yeah, they're different.
They just look similar?
They look similar because the data are.
Okay, but they're unique.
They are unique, yeah. Well, look at the residuals. These, they're arranged differently. Okay? So if you want to see, if you want to visualize the relationship between one of the predictors and the outcome, holding things constant, you do a partial plot. Okay? So if you want to look at that third type of variable, we had demographics, we had some set of variables that we're interested in, but we're not going to control, and that third type of variable, right? We might want to look at that partial plot between that third type of variable and your outcome to show how, holding everything constant, as the greater the intensity of your intervention, the greater the outcome is on average.
What was the command for that? Sorry.
AV plot. And I'll put the code up on Blackboard too.
And you don't usually present these, right? Because you're only talking about like part of the outcome. Right?
Yeah, only part of the outcome. However, this helps convey or communicate the relationship between your real variable of interest and the outcome, holding everything constant. So I might not execute AV plot, but what I might do is get the partials, do the scatter plot, and then the regression, because that's what this is, to show how holding everything constant, this is the relationship between my real predictor of interest and my outcome of interest, to show the relationship.
What does this tell you that the partial correlations do not?
Nothing. This is a visual
It's a visual
representation of the
representation.
partial correlations. That's
Okay.
a good question.
But why, wouldn't it be better if this was a visual interpretation of semi-partials? Or why do you want to be taking the effect out of the outcome also?
That's a good question, because this is just, this is an easier way to plot it.
Okay.
This is what it means to hold things constant.
Because we were talking before that it like, doesn't make a lot of intuitive sense to take the effect out of the outcome.
It does, it's hard to explain to people in words.
Right.
Show them,
Okay.
right? Show them. People can look at a plot and go, oh, I see, as this goes up, that goes up. And you could say this is holding everything constant.
And this is not showing the unique impact of the variable on your outcome?
Yes, it is. Yes, it is.
It's the unique,
That's exactly
okay.
what this is. That's exactly what this is.
And the semi-partial shows you.
So it's, when we say partial, it's the unique between, it's the unique holding the other variables constant in both
Right.
the outcome and the predictor.
Right.
The semi-partial is just holding it constant in the predictor. Okay. Okay, so that's, I think these are interesting. These are useful for explaining things to people. So remember, a lot of times we're interested in doing that. Otherwise, it's just, you know, interesting white ivory tower research. No one reads it. So the extent to which we can better explain things to people, the better. Okay. Okay, so the next thing we want to examine is something called multicollinearity. Right, multicollinearity. And there are indices of multicollinearity. There are several out there, and Stata has one built right into it, and the command is VIF. VIF. VIF stands for Variance Inflation Factor. Variance Inflation Factor. So remember when we talked about multicollinearity, the problem with multicollinearity is that the algorithm, the statistic, doesn't know how to give people variance. When we drew the Venn diagram, we have this area here that belonged to everything, right? Right? And we said, well, we don't know who to give credit to, so we're going to partial and semi-partial stuff out, right? Well, the degree to which our predictors overlap, right? So here I have x1, here I have x2, here's my my predictor here, the degree to which our predictors overlap makes that overlap area obviously bigger. The algorithm doesn't know what to do with the variance, doesn't know how to parse out the variance. As a result of that, the standard errors associated with each of these coefficients will be monstrously inflated. Let's see here. Standard error will be inflated. Standard error is what? It's variance. Variance inflation factor. So the variance inflation factor tells us what is the extent to which the collinearity is inflating the variance of the coefficients. So to do that, all we have to do is say VIF. Okay? So here we have some problems. If we see variance inflation factors of like 8, 9, that means that the collinearity, the relationship with these other variables, is increasing the variance, the standard error of this coefficient by this amount. If I had a variable that was completely independent of the other variables that have a variance inflation factor of 1, meaning it wouldn't inflate at all. Okay? But we see, remember before when we looked at the bivariate plots and age seemed to be correlated with a whole bunch of other things? The relation and the consequence of that is we have this very large variance inflation factor.
Say it again, Edward.
Oh, so we gotta So when we did those bivariate plots, we observed age being pretty linearly related to the other predictors. Right? We said, oh, we have to keep an eye on that because we might have multicollinearity. The problem with multicollinearity is that it will inflate standard errors.
Right.
If you inflate a standard error, what that's going to do, that's the denominator of your t-statistic. So what is that going to do if you inflate the denominator of when you do division? It's going to make the quotient very small, therefore making it difficult to see the true relationship between variables. Okay? So here we see the age, when we did the bivariate relationship, we saw age was related to the other predictors. Here's the consequence of that multicollinearity on age, or of age. These other three predictors combine to increase the variability, the standard error of the age coefficient by a factor of almost 14. Let me be very concrete about that. See this standard error for age? See how it's the biggest? Why is that the biggest? It's the biggest due to multicollinearity. This is about 14 times larger than it would be if these variables were not present in the data.
So, I mean, if the standard error is inflated, it's going to bias your study towards the null
Yes.
for that variable, but like it shouldn't affect the coefficient.
It won't affect the coefficient.
So it just it affects your ability to tell whether something is statistically
It affects your inference, the validity of your inference.
Right.
So this is saying age doesn't have as big of an effect on the outcome as we would have thought.
Yes.
Because these other three are falsely increasing.
Yes. 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 So what is this variance inflation factor? You actually already know what it is. There's a statistic called a tolerance. So this 1 over VIF is what we refer to as the tolerance statistic. So let me write down the formula for tolerance. And let's see if this looks familiar to you. You ready? What's this? It's a coefficient of alienation, isn't it? Right? So if I regressed age on size, weight, and height, I would get an R squared of 1 minus this. So what's 1 minus that? 93, 92 and change, 92, 2? Does that make sense? So these three things combine to predict over 92% of the variability in age. 92% of the variability in age can be predicted from height, weight, and brain size. This is our variance, this is our tolerance, which we've also heard it called coefficient of alienation. 1 over coefficient of alienation is your variance inflation factor. That's all.
We're doing 92%?
1 minus 0.72589, right, would give me R squared. Does that make sense? Let me show you.
And so you can also say that age predicts 7% of the variance in IQ?
No. To answer that question, I go back to my partials. Age explains the unique amount of variance that age explains in IQ is 5% greater than that of height, weight, and size, brain size together.
And this does not take into account the fact that the other three factors influence it so much.
This is just the relationship between the predictors. I haven't looked at the outcome at all in this, for looking at the variance inflation factor. When we look at variance inflation or multicollinearity, we're simply interested in the relationship between the predictors. We're ignoring the outcome.
So then can you say to yourself at this point that maybe you shouldn't include age?
Well, that's a good question. Let's talk about this. What do we do about it? Let's finish this and then we'll get back. That's a great question because that's what I want to talk about next. Okay, so what I'm going to do is I'm going to regress age on the other three predictors, right? And I get my R squared. What did I say my R squared was going to be? At 93%. 1 minus 90, 97 or 92, that is going to be that statistic. 1 over the reciprocal of this is the variance inflation factor. Okay? So part of your homework for Stata Lab is taking into account these post-estimation commands. This is how I grab the R squares. Boom. So I did the regression. I pulled the R squared from the regression. This is the R squared. 1 minus R squared is that. That's the tolerance. Okay?
So I mean, you're regressing age on the other independent variables.
Yep.
But
I'm ignoring
you get an
the-
R squared, but you already knew what the R squared was from tolerance.
Yeah, I'm explaining how we get that. That's what I'm trying to do. You already know what this is.
No, this is just the process of what gets you to the
The VIF.
the VIF. Okay.
The variance inflation factor.
Could
If
you
you-
say,
Yeah, go ahead.
could you say again in words what that 13, how you state the interpretation of that number 13?
Yeah, the variance inflation factor. So the collinearity of age with the other predictors is inflating the standard error of the coefficient for age by a factor of about 13.8, thereby making it more difficult to see the true relationship or to reject the null hypothesis. But to Sam's point, the beta coefficients are unbiased. The beta coefficient, the parameter estimates are right, the standard errors are wrong. But we need the standard errors to make inference, statistical inference. Okay? Okay. All right, so here's what I'm going to do next. I'm going to use more of these post-estimation commands and I'm just simply I'm gonna repeat the regression I did above. I'm gonna get the y hat variable, and I'm gonna get the residuals. And then I'm also gonna get the standardized residuals. So let me move this over, and after I run these commands, we see 3 new variables were created. A y hat, these are my predicted values. These are gonna be my residuals. And then I'm gonna get my standardized residuals. So all I did was I turned these residuals into z-scores. Right, Stata did that for me. Then let's talk about the assumption. Why am I interested in doing this? Because remember we talked a long time about the assumptions, the distributional assumptions of our error, of our residual. Let's see if you can help me write this out here. So our error is normally and independently distributed with an expected value of 0 and constant variance. So let's examine those assumptions. Okay, so what I'm going to do is I'm going to create a scatter plot of my residuals against my predicted values. Right? I want to see, I'm going to use this to examine the constant variance assumption. Okay, so when I do that bivariate plot, oh my God, look at that. Those are my residuals. So, how about that? That's pretty cool, huh? Mathemagics, folks. These are the residuals for this data set.
That's pretty awesome.
It's pretty cool, huh?
I was wondering why there were boxes around your AV.
So, do we observe?
I was like, how did this random data get in?
It's, we have tricks. We have to keep you engaged, otherwise you fall asleep. So what do we think about this constant variance around the regression line? So if the variance were constant, we ought to see more or less a uniform distribution around 0. You satisfied with the homoscedasticity assumption? Yeah, I'm not either. What I observe is as x increases, I see more variability, right? Because we have these, there's more variance at the high end of the x scale than there is relative to the y scale. Right? So we have violated, there's pretty good evidence of violation of that homoscedasticity assumption, which means that the precision of our estimates are not constant. Right? So there's more variability as we go across x. Okay.
So,
yeah.
This is showing residuals for the model as a whole.
Yep. Whereas the other ones, the A/B plots, were the residuals from the other variables partial. Okay. But in the end, it really always gets back to bivariate correlation, doesn't it? It always gets back to bivariate. Okay, so now let's look at the normality. I'm going to use the mouse and I'm trying to point to the end over there on the board. So all I'm going to do is I'm going to get a histogram. I'm going to get a histogram of my residuals, and then I'm going to plot. I'm going to superimpose a normal curve on that histogram. Okay. What do you think? Do we have a normal distribution of our errors? No, we have a bimodal distribution. We have a bimodal distribution. So we have violated our normality assumption. You guys feeling good about your regression so far? What are the problems so far? What do you think? We violated normality, we violated homoscedasticity. Anybody have any insight? As we examine the assumptions, do these data appear to fit our model? They don't appear to fit our model. So we need to start asking ourselves, something's wrong. We acknowledge something is wrong. Are the data wrong? Or is our model wrong? Our model being how we believe the world works. What's most likely the case?
Our model's wrong.
Probably our model is wrong. It's also worth saying that all models are wrong. Some models are more useful than others. That's another famous statistical quote. But these data do not fit our model. Our view of the world with respect to IQ in this case suggests that there's probably a better model that would describe the relationship between, that would allow us to explain the variability in IQ. The other thing we can look at is what's called QQ plot.
Can I just ask a question? So how, if you're reading a paper, I mean, usually people don't
No, they
report
don't.
that. So
No,
how
they-
would you assess that?
You can. This is the problem with rushing through statistics courses, I believe, is that, we could just, it gave us an answer, right? It gave us regression coefficients, and that's where people stop. They don't talk about, well, how good was my model?
Isn't that what the journal's supposed to do with their statistician?
Please.
No, I'm serious. Isn't that like why?
You know who the statisticians are? They're other people, they're buddies of the journal editor.
Okay.
Come on, it's the good old boy network.
So this is not reviewed at the.
I mean, some journals don't even have bias filter.
Oh, I just put that.
I just know New England Journal and JAMA do. But
Well, JAMA, that's JAMA.
Right.
That's JAMA.
Okay.
Okay, all right, so this is what we call a QQ plot. So if our data were normally distributed, these dots, all of these dots would be right on this line here. All of these dots would be right on the line here. So here we see we are under-predicting. We tend to under-predict at the low end of the scale, and we tend to over-predict at the high end of the scale. So it's the tails of our distribution that seem to be wonky. All right. And it's 10:20, so I will stop here. I will post this code out onto Blackboard. The regress data set is out there. Start giving it a shot. In the code that I've given you, in lieu of a PowerPoint presentation, because I don't think you can learn statistics through PowerPoint, that's just my opinion. I did